All right, so good evening, dear colleagues. Thank you for being still with us at this relatively late time of the day. So we are going to start this panel on devoted to genome privacy. My name is Jean-Pierre Hubaux from EPFL Switzerland. We have gathered a panel of distinguished specialists with extremely high complementarity in their background and skills, as you are going to see. I'm going to introduce them in the order at which they are going to talk. Each of them is going to deliver a short presentation in the amount of time that has been left to us, and then we'll have some discussion with the audience. The first speaker is going to be Jacques Fellay from EPFL, a geneticist who is also working at the Lausanne main hospital. The second is Effy Vayena, he is an ethicist working at University of Zurich. Then Emiliano de Cristofaro from University College of London will provide us with the perception of the computer scientists and will give us an overview of the solutions that are envisioned to address the challenge of genome privacy. And then finally, last but not least, Jurgi Camblong is an entrepreneur, the CEO of Sophia Genetics, a company that does genome visualization, and will tell us his perception of genome privacy. As a change to the other panels, we have decided to stand while we talk to make also the session more lively. And so the first speaker will be Jacques Fellay, whom I invite to start this panel.
So good afternoon, everyone. As Jean-Pierre said, I'm a mix between a medical doctor and a genetic researcher, which puts me in an ideal situation to try and envision the challenges linked to patient data privacy, just to make sure we can continue doing research, we can confidently care for patients, and everybody is happy at the end of the day. That's not the one. Yeah. That's Effy. So my mission is very simple, but can be a bit tricky because I've been asked to give you the background on genomics, to put this audience on the same line to understand what my distinguished colleagues have to say. And this is not that easy because this is a very diverse audience. And it will be a bit boring for those of you who know about genomics. And the problem is that many of you don't know much about genomics, so we'll try to get you on the same page. So first of all, we have to define what is genomic data, and maybe the first question is, why do we need a separate session? We talked about health-related data for the best part of the day in this room. Genomic data is health-related data, but it is much more than that in a sense, because it is the ultimate identifier for everybody, which means that we have to treat it a very special way. We cannot just say it's yet another health-related data. And why today do we speak about genomic data in healthcare? It's because we are at this moment in history where we can start using it in the clinical world. So far, we mostly had the hype of personalized medicine is around the corner, lasted for the past 20 years. Today, personalized medicine starts entering hospitals and clinical practice. And this is taken from a Nature review to celebrate the 10 years of the decrypting of the first human genome. And Eric Green and others just tried in a schematic way to represent where we are on this scale. And this was the understanding the genomes themselves, doing the basic research linked to understanding what is in our genomes. And the more you go to the right side, the more you are doing something closer to the patient. And they were careful enough not to put precise dates on every step. But you can see that now we are in this area, 2011 to 2020, where we start having the dots really close to the patient. But we prepare the field for the larger adoption of genomic-based medicine, which will take decades. So the genome, you've got many copies of that in each of your cells, 3 billion base pairs, coding for about 20,000 genes. The genes themselves are coded in a very small fraction of the genome, so we have 98% of the genome that does not encode genes, but encode mostly regulatory things that will make the gene work one way or another. What we learned over the past 15, 20 years through those big genomic projects is that we are different, and we are different in the following way. We all have about 4 million differences in our genome if you compare it to the reference you find online. So 4 million sites out of the 3 million bases will be different between any one of you. And most of those differences are single nucleotide variation, which means a letter is changed from an A to a T or from a G to a C. You know, we have 4 letters, A, C, T, G. And those single nucleotide variants, SNPs, single nucleotide polymorphism, are the bulk of genetic variants that make us different in all aspects. We also have larger scale variants, which are called structural variants as well. No need to go into the details, but those, in theory, have the potential to contribute more individually because they are larger, so they can touch larger places in our genome. A SNP, or SNV, single nucleotide variant, is simply that, I told you. A place in the 2 chromosomes, this is one chromosome from the mother, this is one from the father, and you get sometimes the same letter on both chromosomes, sometimes different letter, and variable sites are single variant. How do we read that? We used different technologies that can be schematized in those 2 categories, genotyping or sequencing. Genotyping is the art of only looking at the places we know are variable in the genome. Sequencing is going brute force, reading the whole genome. Both of them give pretty much the same results in variable sites. You get a catalog of all the variation in a patient, in a population. In summary, what you have in a genome, I told you about 4 million variants, 3.5 million of them are single nucleotide, and a small number of them have the clear potential of being destructive, meaning that some of our genes are not creating proteins because they carry stop mutation, knockdown mutations. And those are responsible for Mendelian diseases or could be responsible for very specific reaction to drugs, for example. So those are low-hanging fruits we like to explore when we do genomics. And we have hundreds of thousands of larger scale mutation, as I told you before. Again, we can categorize them depending on their predicted functional impact. So what do we do with all this information we can today gather on our patients or on yourself if you want to do preventive medicine? We can today sequence the genome of people, mostly kids in hospitals, that have weird symptoms. You have kids, you don't know what they have, and the ultimate resort is to just go and sequence their genome, and sometimes you find a mutation that is never observed before, and suddenly you have a potential explanation for what's happening. Those programs exist in different countries now, and have been very instructive for people doing genomics because it shows that this tool is today available and usable. Pharmacogenetics is also a primary target because we have variants in our genomes that will make a drug work better or worse, create adverse events or not create adverse events. And there is, for example, this catalog by the FDA, the table of pharmacogenomic biomarkers in drug labels. There are 170, maybe 200 now gene-drug pairs listed, involving only 40 genes out of 20,000. So there's a lot of research still to be done. And that's why we're only at the dawn of genomic-based medicine, but slowly entering it. Cancer genomics, that's also something that starts being used large scale in several hospitals. A cancer is by definition a genetic disease. It's mutation, somatic mutation that will lead to dysregulation, tumor formation. So it's only natural to just sequence the cancer, sequence the normal genome of the patient, find what went wrong, define the better therapy based on that. And that's happening today. Those are a few examples of what I told you about Mendelian diseases. This Volker boy had 100 or more surgeries before they decided to sequence his genome. They found a mutation that usually did not lead to the symptoms he had, but they could decide to go for bone marrow transplant because of the mutation they identified. Since then he's doing well, and he was about to die before. So that made the headlines before because it was the first one in 2011. This researcher sequenced his own leukemia. After he was working on leukemia, got the leukemia, sequenced it, and found a drug that wasn't labeled as an anti-leukemia drug, worked fine, is in remission. And recently, a few months ago, there was this paper by the neighbors in the Netherlands finding the explanation in more than half of the cases of severe intellectual disability that couldn't be explained before genome sequencing. So we can do something in the hospitals today. Tomorrow, and maybe later today, because some of it is already entering the clinic, it goes fast, neonatal sequencing, ethical questions linked to that. Should we sequence all babies at birth? For medical reasons, why not? For all kind of other reasons, probably not. Maternal blood sequencing, that's a very neat technology where you don't need to do amniocentesis anymore, which is responsible for some miscarriage, because you can get the genome of the fetus by only sequencing the mother. Do you sequence the plasma of the mother to get the genome of the baby only to know about very severe Mendelian diseases, or do you do it for cancer risk prediction or Alzheimer prediction? Direct-to-consumer genetics, DTC, that's something that happens outside of the healthcare system, but patients start arriving at my practice and they show me their 23andMe results and say, doctor, what do I do? That's something that is happening and will happen more and more if DTC is resurrected. That's another question. After tomorrow, complex trait genomics. The genome has 4 million variants for each of us. All those variants, one way or another, could be combined and contribute to all our risk for complex traits like diabetes, like aging in general, hypertension, you name it. And this is not yet ripe for clinical care, but will arrive and will also come with a whole lot of ethical and privacy issue, because again, you can identify perfectly any human being based only on the genetic data. You don't need anything else. Genomic data is the basal layer. Here I just list, for the sake of completeness, all the other layers that are around the corner. We have the DNA, which is the genome, but then we have the transcriptome, RNA, that's the next layer. The RNA is then translated into proteins, proteome. The epigenetic regulation of the genes is also an interesting layer that we can read now. Metabolome, product of degradation. Metagenome, that's all the bugs that live with us, on us, in us, and that contribute to health and disease. And all that together will be the big data, the big omic data that we have to deal with in the near future. And the perspective is very simple. Genomic-based medicine is around the corner, no question about it. There is a considerable space for new genomic market in health, but not only in health, in nutrition, in well-being. So it is a huge market opportunity, and it's only the beginning of the big data-based personalized healthcare. And for all that to happen, we need trust. And that's not original to say, but that's really the basis of everything we want to discuss about in this panel. Thank you.
Let's move maybe to Effy. We'll take probably the questions at the end for the sake of time.
Okay, well, thank you very much for the opportunity to be at the panel. It's been a great day with a lot of interesting discussions already going on. So I was tasked with just talking about the societal implications or the special issues that arise in relation to genomic privacy. And I thought, what a better place to start from a general idea, sort of a general idea of privacy, and my starting point in understanding some of these discussions. So I do start in general from the human right to privacy, which is in Article 12, and which calls for no one to be subjected to arbitrary interference with his privacy. Now, maybe you all should make a mental note to the word arbitrary interference. That creates a moral basis and creates, if it is a right to, we do have a right to privacy, then that generates duties to others to respect it. And of course, beyond that moral definition or moral basis of privacy has been translated into legal rights, which so many of us have talked about today. It's understood in different ways and complementary, not necessarily antagonistic ways. As we heard earlier in a great comment in the previous session, in thinking about privacy, and even in thinking about privacy as a right, it's important to understand that this does not antagonize the common good. And in the debates we have here, it is about privacy as an individual right and privacy as part of the common good. So make also that other mental note. Now, a couple of things that are important. Clearly, we're living in that digital context, and that applies to genomic as into everything else. Since in this room there have been a number of philosophers that have been quoted today, I think it's absolutely okay to quote Luciano Floridi. In his new book, he talks about the context, which is the situation where we're in at the moment, where we live in this infosphere with no outside. Going back to the right, even the United Nations, the Human Rights Commission is looking at the right to privacy in the digital age, because things are different and we have to evolve our understanding around how we're going to address the issues that we have to face. Now, the next part of the context that we live in, and that's very relevant to genomics, is that we live in a sort of a sharing context. And that is happening at two levels, I think. One is at the institutional level. We hear from our researchers and organizations that we should share genetic data and a lot of other data if we really want to promote medical research, public health research, and our understanding of knowledge. The NIH, just an example here, there are many more organizations, of course, promoting the idea of sharing the data we collect, has issued a policy encouraging researchers, actually requiring from researchers to share genomic data that they have collected, moving away from the model where the researcher collects their own data, they do their own analysis. It's a lot more people who can actually tap into that wonderful source of data. But we're also experiencing the sharing context in a different way. We have the individual sharing. So Jacques mentioned before the direct-to-consumer genomics. There are many more ways that today somebody can access their genomic data. They are outside of institutions. And with the decreasing costs of technology, they will probably be easy to have this kind of access outside of institutions. And then people will be sharing their data in ways that maybe we haven't even thought about. So sharing is going on. And then the linking context is also relevant, because we're again thinking about how we'd be linking data. This is one of, I think, quite highly cited or highly viewed a graph that was published last year in JAMA, and it shows how many different data sets we would ideally like to link and analyze in order to generate very valuable health information for an individual. And if you are able to look at the slides and maybe read it, it actually refers to all sorts of different data, one that are totally unregulated, others that are highly regulated, some are very sensitive, others are less sensitive. But the idea behind this is that would be, as they refer and they're relevant to the individual, if we're able to have them in some sort of way, we could it could be very useful for that individual, and if we were able to use those tapestries of data of many people, then that would be, we would have real breakthroughs in research and in our understanding of health and disease. Now, just a bit more specific to genomic data and the information that we can glean from this data. Usually, I'll just think about how we tend to think of those. So we can identify people through that. Jacques said that it's the ultimate identifier or fingerprint. We can expose somebody's condition, for example, and we can predict something about their future. So all of these things we can do with genomic data can cause harm. They should not necessarily do that, but they create the possibility of harm. And the harm that we're quite worried about often is that of discrimination and stigmatization. Now, in those discussions about genomic data, we tend to think of those categories, for example, insurance, either health insurance or life and disability insurance, how genetic information can impact on those important aspects of one's life, employment, whether that's appointment or career development. And of course, in many countries, those at least aspects of these areas are highly regulated. So you cannot do certain things. You could do other things. So for example, you could do less here, but more here. So it's still, although it is regulated, there's still room for potential harm to people. Now there's a separate category, I put it under a separate heading because I think that's less regulated and probably hard to regulate. This information could have implications for people's social interactions, for their integration into social groups or their relationships. And we don't talk so much about the last one, but I think it is a potential implication. Now, typically what we're worried about, it looks like this. Somebody would be declined life insurance because of a genetic information that their insurers obtained, but then you could go to a court maybe or to a commission and have some better treatment. I don't know how many of you followed that story last year, people who find relatives in the genomic databases, those of, for example, consumer genomics, somebody who found that shares a large percentage of the DNA with somebody else who was unknown to them, and it happened that it's his half-brother. So secrets are coming up. He wrote a very interesting blog calling that, "With genetic testing, I gave my parents the gift of divorce." So that's just another kind of implication. I mean, I'm not making a judgment whether these people should divorce, whether secrets should be there, but what I'm trying to say is that there are a whole range of issues for which genetics can play a special role. Now, these are sort of the kinds of harms, when we're thinking about harms and potential implications of genetics, I'd like to also include something else, which is the privacy, for example, violations, but no harm. So let's say we have data, genomic data accessed, they're not used, they're just simply accessed. They're not published, and there's no secret. Is that a problem, or would be all okay with that? Of course, we're worried about harm, because that is worth more worry. But in another discussion, which I think we should bring over to genomics as well, is that the mere fact that that private sphere is accessed by somebody else, it constitutes a problem. And I would like again to think of of privacy as this having the self-constitutive value and allowing people to form their own personal identity. So it is not just about causing harm. There is more to think about when we talk about privacy than harm. How we are trying to deal with this, I guess today in the debates that we heard, in the discussions we heard, it seems that we try to have a socio-technical solution. So technical solutions to increase security, for example, of data, better protection and security. I think my colleagues will talk about cryptographic techniques, statistical techniques that seem to give us a technical solution and opportunity. Others who've talked about consent options, not simply a tick off the box today for what's going to happen forever, but options that allow a more dynamic relationship with people's genomic information. They follow the life cycle of data, they put tag, they put sticky policies. I think we should be cautious again when we talk about consent options and try to equate that with control, to remember that consent and that kind of control is just at one stage of the process. There's more control we might want to have. At the societal level, however, as much as the technical solutions can do for us, I still think the questions we're dealing with have this large societal component, and maybe we need solutions at that level as well. So we need to, if we anticipate that, and we're worried about the harms from privacy violations, which even in our best case scenarios, they may happen, we need to be prepared to try to minimize those through other means. Criminal law, for example, we have some, but it's not comprehensive. We should be able to redress the harms from privacy loss when it happens. And I think we should be thinking also about more systemic changes. People who worried about harm because they're going to have no access to health insurance is mostly also because maybe they don't have universal health care coverage, or because their health care is not adequate in the system they're in. So there is more to think about than try to have one solution for this very complex problem. And I think when we're talking about discrimination, at least at the social level, at the personal level, it is important to increase people's genetic literacy and genomic literacy to understand what really means to have a trait, or what its impact going to be in a number of things in a person's life. I'm going to close with a paper that I read recently, and it is by Ehrlich, who many of you in this audience may know. He does work on re-identification with genomics, and I very much like the title because he called it Redefining Genomic Privacy, Trust and Empowerment, and these are wonderful words. Going on to read the paper, it seemed to suggest that we should move from privacy to trust. Ways that the paper suggested we should do that are, again, very interesting, and I totally endorse them. More transparency, because yes, we have more transparency with trust, more trust with transparency. Increased control, which is very important, and reciprocity, because these also could maintain the trust we managed to establish. The question that it raised to me, and I want to throw it out to you as well, is whether we can have trust without privacy. If we're really moving away from privacy, can we get to trust? I can see how we can move maybe slowly from control to trust, but I'd like that would be something to discuss. Can we go there? My own views on that are that, yes, clearly we need to reinterpret privacy in the digital context and digital genomic context. Maybe we need to redefine how to protect it. Maybe we have to renegotiate, not maybe, certainly have to renegotiate what kind of trade-offs will be acceptable. We have to enable real control, not just a better consent form. We have to see control at the governance level of what we're doing with people's data or what we're doing with their genomic data in the decisions we're making. And finally, again, I will use one more quote from Luciano Floridi, that the value of privacy is both to be defended and to be enhanced, and definitely not to be abandoned. Thank you.
All right, thank you very much. Thank you, Jean-Pierre, and all my colleagues in the panel. It's really an honor for me to be here and give you my perspective, that of a computer scientist, on genome privacy. Just get this one. So we heard really great overview of advances in genome sequencing and genotyping and genomics in general from Jacques. And as a doctor and geneticist, when Jacques sees genomes, he sees probably bases, right? This double-stranded polymer of nucleotides, but a computer scientist really sees a file, right? An annotated file, a sequence of bits, strings, you name it, right? So this is a SAM file, right? So we can really say that once we have an annotated file, doesn't matter what kind of data it contains. From a computer science point of view, we need to work on mechanisms to store this file and to give people that need to use this information, so Jacques and doctors and clinicians, geneticists and so on, ways to extract meaningful information from it. So run tests, queries, search these files and so on. And so far nothing really new, nothing really exciting. Perhaps except for the fact that if we do whole genome sequencing, these files are very, very large, right, in the order of gigabytes. But in reality, we are all at a privacy conference, and we know that not all data are created equal, right? So we already heard that a genome is an ultimate identifier. It's really a unique identifier, right? And this makes it very hard for us to anonymize them. To remove identifiers from genomes. And from a security point of view, really, it's interesting to notice that there is many types of information that are very sensitive. They are contain a lot of identifying information, but usually we have some mechanism to recover from potential data loss. So if you if you leak your password or your credit card information or social security number, you have some ways to issue a new one. Well, you cannot really do it if your genomic information is out there. You cannot just issue yourself a new genome. Well, I wish I could do that. I will change a couple of things, but unfortunately we can't do that. I probably don't have to work very hard to convince you that a genome is really a treasure trove of highly sensitive information. So if you get a hold of my genome, you can easily get information about my ethnic heritage and perhaps my predisposition to diseases, including mental conditions, right? So, we need to reaffirm that. And again, one very particular aspect of genomic information is this correlation between, it's hereditary information. So if you get a hold of my genome, essentially you get a hold of my relatives' genomes as well. And so actually I have a question for you. Who knows this picture? Yes? Yeah, okay, yes, that's good. So this is a very famous case where, the genome of this lady, Rita Lacks, was published, and, the family was quite upset about it. And Jean-Pierre and his colleagues have actually formalized and studied the concept of kin genomic privacy, so looking at the relationship between, one's genome and that of close relatives. And you can read the paper, of course. And so, this brings me to the next point, that there is essentially the sensitivity of human genomes is almost perpetual, right? So, 100 years from now, I might not care if you get a hold of my genome. I will probably be dead, but, my future children and grandchildren might care, as we just said. Our genomes will be very, very similar. All right, so in the past couple of years, we really witnessed a rise of a new research community. And again, I'm focusing on, with a computer science perspective, right? So from a computer science perspective, and especially from the security and privacy community, we have seen two main directions in research. So the first one is really to study, analyze the privacy implications from a data point of view of advances in genomics in general. And this is mostly bad news, unfortunately, and I'll give you some examples of that. And the second one is a little bit more promising, more exciting for us. And really, there is a whole community that looks at ways to actually protect privacy and enforce security of genomic data. So we are exploring a number of techniques. So let's start with the bad news. So probably, the most popular result in this space is the work by Melissa Gimrek and colleagues that looked at ways to actually re-identify anonymous DNA donors. So, you might think that, if we have genomes, we remove all information that we think can identify the genome's owner, and then the genomes are anonymous. Well, that's not really the case. So these researchers were able to actually reconstruct the DNA donors down to their surname. And there's been a lot of press coverage for these results, but there's actually many other results that look at similar issues. Okay, so we just said that anonymization is very hard to achieve, doesn't really work. So what about aggregation, right? So if you put together, thousands of genomes, can you still extract statistical information, for instance, about the correlation between SNPs and diseases? And can we do that so that we can really go back to the identity of the donors that compose these aggregated data sets? Well, not really either, unfortunately, and there are results that actually date back to 2009 that showed how even statistics from allele frequencies can actually be used to identify genetic trial participants. So again, re-identification of donors. And if you're interested in this topic, you can actually read an interesting paper that was published last year that kind of systematizes the different ways, the different routes that you can use to breach genomic privacy. Okay, so now I'd like to switch gear and go a little bit more to the more promising results. So I'd like to ask how many of you have heard of differential privacy? like a fair number. So without going in the details, differential privacy is rigorous technique that, roughly speaking, allows us to add noise to statistical databases so that we can actually maximize the accuracy of queries to statistical databases while minimizing the chances of identifying its records. So this is really a very, very generic definition, but it's an actually pretty rigorous mechanism that allows us to protect privacy of single records and, for instance, single donors in the case of genomic. So there is some promising results in this space. I'd like to highlight one of them. It was published a couple of years ago, almost in KDD, that uses differential privacy to support genome-wide association studies, where roughly the idea is to allow researchers to compute, for instance, number and location of SNPs associated to diseases in such a way that these queries do not reveal information about the single record, so we cannot violate privacy of patients. There's also another line of research that Jean-Pierre and myself are really involved in that look at things like privacy-friendly personal genomics. So we have heard a little bit from Jacques the advent of direct-to-consumer genomics and a lot of personalized medicine results. So we're looking at mainly two avenues to achieve that in a privacy-preserving way. One is to actually let users, individuals, patients, have control over their own data. So we let them have an encrypted copy of their genomic information, let's say their whole genome in case of whole genome sequencing, but yet we allow doctors, clinicians, researchers to run some queries, to run some tests on this data, and we use some cryptographic protocols, roughly we call them secure function evaluation, that allow them to actually run these tests like personalized medicine, compatibility testing, ancestry testing, and so on, in such a way that only the test result is disclosed and nothing else. So we call this as a kind of a minimum required amount of information that is disclosed in the process. Another approach is to rely on a storage and processing unit where, after data is, I don't know how to, okay. After the genome is sequenced, we can collect some data, like SNPs, encrypt them, and store it at the storage and processing unit, and yet allow doctors, for instance, at a medical unit to run tests, for instance, like predisposition to certain diseases. Again, in such a way that nothing is revealed about the data wholesale, nothing is revealed that can harm the patient's privacy. Okay, so there is a number of open problems that we are working on. Again, strictly speaking, from a computer science perspective. So I'd like just to point out some and maybe offer some ideas for discussions during the rest of the panel. So one issue is really how, if we rely on encryption to protect the security of genomic information, can we really guarantee its security past, let's say, 30 years? We know that even if we use the state-of-the-art encryption mechanisms with the longest possible keys, still we cannot guarantee security past, let's say, 30, 50 years. One other thing that I like to point out is the fact that we're clearly talking about issues that involve the user, the patient. So, and I think there is a lot of usability issues, not only with respect to, let's say, informed consent, but also whenever we have technologies that involve the users, we have user interfaces and we have user perception, and we have to take those into account. And of course, there is more related to the overhead that cryptography introduces, as well as data representation assumptions. So a lot of our cryptographic protocols, make some assumptions about how the data is represented that sometimes contrast with how doctors and geneticists actually work with. So getting ready to conclude, I also want to do some little bit of advertisement and invite you all to participate in a workshop that it's now at its second edition. It's going to be co-located with one of the largest security and privacy conferences, IEEE Security and Privacy, and it's going to be held in San Jose, California in May 2015, May 21. And we are currently accepting submissions for short and long papers. Submission deadline is just in a few days. And if you would like to know a little bit more about genome privacy, again, from a computer science perspective, I recommend this website where there is a very good collection of papers and on the topic. And also, we wrote some kind of survey of all these issues that I invite you to read. Well, thank you very much.
Ladies and gentlemen, my name is Jurgi Camblong. I'm a biologist, an entrepreneur, and a dreamer as well. And basically my dream when I started that company now 4 years ago was to help any hospital make use of next-generation DNA sequencing technologies to simply better diagnose and treat patients while respecting the privacy of the data. So, as you heard from the panelists, we are in a very exciting world where there is a big momentum around genomics technologies. And this momentum is reported by governments as well. And I don't know how many of you have heard about an initiative called Genomics England here. Could some of you know it? Yeah? So I think this is one of the most amazing and ambitious government initiatives right now. Very innovative. And considering especially the financial crisis we are in right now, David Cameron has given a grant of £300 million to basically sequence 100,000 genome from now to 2017 for two purposes: better diagnose people, but as well produce data so that researchers and companies can as well innovate on data and find new drugs that could help people being better treated. Similar initiatives are taken in other countries, and I think the fact that governments really push into that direction shows a lot about the potential of these technologies to improve healthcare systems. Another point I wanted to highlight is you may have all heard that Angelina Jolie has been tested for breast cancer predisposition recently, and I think this has created a lot of awareness around what genetic testing is about. I think the action was quite brave because, it's not easy for a woman to go through such type of testing and potentially surgery. And this is as well another example showing that basically there is awareness about around these technologies and that these technologies are starting to be used. Another company you may have heard in the field is called 23andMe. 23andMe is one of these direct-to-consumers companies that was highlighted by Jacques and who has already basically tested over 100,000 individuals in his history. So I think we are at the crossover of a very exciting time where digital technologies will be used by hospitals to better treat patients. This will start with next-generation DNA sequencing. And this can happen thanks to things that are invented in another word that is a word I didn't know until recently, which is the word of high-performance computing. And the merge of these two technologies is going to enable us to go towards what we call the P4 medicine, which is a medicine that is personalized, predictive, preventive, and participatory. And this is going to enable us to better diagnose patients, which I think it's extremely important. Why? Because today we basically give poison to patients. We don't target the right drug for the right patient. So diagnostics is really important. When you go to the garage and you have to fix your car, they first do a diagnostics, right? They don't start fixing the car before doing a right diagnostics. And this is what digital technologies are going to enable today. So basically, this design represents the change of paradigm that we are facing now. So we will move from a one-size-fits-all approach to a targeted therapy. And people use the term of personalized medicine. We right now use rather the term of precision medicine. Right? It's a medicine where basically we better diagnose patients, and based on the diagnostics and the drugs available, we give the one who has the best chance of working for that patient. So obviously this is a very exciting trend as well for people who have launched companies, and I wanted to share you one figure at least so that you can have a sense of the market interest there. And until now, genetic testing was mainly used in research, and as you can see in 2012, the business volume of this activity was about $1 billion. We'll reach in research field about $3 billion in 2022, while the diagnostics market is really growing fast. And this is due to the fact that these technologies are finally being used in hospitals to better diagnose patients, and not only in research to understand how life works and what are the secrets of DNA. So it's a very dynamic and fast-moving environment where researchers are very active thanks to grants, but where companies are very active as well. It's a market which is at the stage of automotive industry in the 50s, so nobody knows how the future will look like. You have companies who are offering one-stop shop solutions, and you may have heard about one of them called Foundation Medicine, who just announced a big deal a few days ago with Roche. These companies' assets are the processes they have and 30,000 patient data they have analyzed, and they are worth $1.4 billion in the NASDAQ. So this gives you a sense of the interest of all these companies going into that. The difficulty today for an hospital, when an hospital wants to go into routine next-generation DNA sequencing testing, is that due to that there are plenty of factors. Some of them are the fuel, some of them are the car, some of them are the highway, and nobody really knows what are the best technologies. And so my dream was basically to help hospitals make sense of that. And the way we address that, rather than thinking about processes step by step, we address that thinking data. And so what we do and what we believe the whole community needs to be doing in the field is work together, share the data in a trusted environment, and based on this data, build machine learning and pattern recognition principles that can really help go further and precisely diagnose patients. And any data that are being produced today are actually very useful. You know, the fact that we don't mutualize this data is a waste for the society. We're just basically paying our drugs far too expensive because we need to do clinical trials. But in fact, we could even estimate that we are all part of a clinical trials. And we have heard some speakers previously talking about such type of things as well related to epidemiology. So I wanted to share with you where hospitals are today, because I think we all hear a lot about genomic sequencing and the excitement around, but I wanted to really bring you down to earth. And this is where my dream started to become a reality. We have been in a position where we can today help hospitals with very simple things, and helping hospitals with such simple things as help patients to be better diagnosed and treated. That's a case of a German hospital who has been working with us. They moved their technology for analyzing 2 genes related to breast cancer predisposition from a technology called HPLC to DNA sequencing. And normally a given hospital would have needed about 6 months to 1 year to do that. And thanks to principles of data sharing, machine learning, pattern recognition that were implemented, we've been able to help them move forward in 2 weeks' time. And thanks to that, now they can analyze patients with a better technology. In parallel, Another example I wanted to share with you is a case in Paris, in Hôpital Saint-Antoine, where basically a very brave lady called Véronique Barbu is analyzing thousands of patients suffering from biliary disorders. And if they are well diagnosed, these patients can receive a drug. Today, due to the limited budget she had and the complexity, political complexity of the institution, she would need it 9 months from sample to report. I think this is really criminal. And these people are waiting for being diagnosed and treated. By chance, we get to know her, and now she can do it in 4 days time, and not only for 1 gene, but for 10 genes. The last example I wanted to show you, Jacques told us about cancer. Indeed, cancer is a genome disease, and this is where next-generation DNA sequencing will be the most used, actually. And there will be some privacy concerns, because obviously the tumor DNA will give some insights as well of your DNA you have from birth, and so some family indications. But just to show you that these technologies are a must today. We have to protect the information, but we have to use them. That's a case of a patient who basically was tested for leukemia, and the hematologist could find a mutation which was only present in 5% of the DNA molecules. And since leukemia is a blood cancer, what you can do is that during the treatment you can take new samples and do again an assay and see whether these mutations are disappearing. And this is where NGS technology can enable you to do such type of things, because you can go as low as 2% variant fraction and see that indeed the cancer is dying because the mutations are disappearing. So another reality is that this field, as I told you, it's like the automotive industry in the 50s. There are no standards, and we didn't wait on public authorities to build the standards. So we help hospitals build their own standards and go forward with some validation programs, which helps adoption of such type of technologies. Ultimately, I think this leads to a great potential of several hospitals who can work, who can basically not only share the raw data they produce, the knowledge they have, but who can as well do something which is very important, and this will be my most important slide actually. The more we will sequence DNA, the more we will detect what we call variant of unknown significance. We will have plenty of them. Jacques told about 6 billion of letters, but the type of variant you can encounter is massive. It's not only the 3 million that are different from one patient to the individual to the other. Each time you acquire a cancer, you may acquire new mutations. And the only way the community can make sense of this variant of unknown significance is working together already today while patients are diagnosed. And for this, a trusted environment is very important. And it has to be trusted not only for the privacy aspect, but as well for the quality aspect. And the data that are entered in any common community system and that will be used to classify such type of variants have to be trusted. So just to finish, there is no doubt that trust is key in this field. And there is no doubt that basically healthcare system will move to what I call a sustainable system, where patient information today will benefit to better diagnose the patient tomorrow. And this will be the case certainly for DNA information, but as well for any type of information that will be added on the top of that. So thank you very much for your attention.
Merci. Thank you, Jurgi. So you got 4 presentations on, from very different speakers with different backgrounds, and yet all 4 very aware and very engaged on the topic of protection of genomic data. So I would suggest we now open the discussion to the floor and take, let's say, questions from the audience. Sure, Mike. You want to introduce yourself?
My name is Atta Badi from University of Reading. I just wondered why we should have a lot of complexity in this. If we look at the patient-centric perspective, a patient has to merely know his propensity to develop certain diseases once, and remember those. You know, I mean, once the genome data has been processed for a patient, the patient can look at it with their medical practitioner, etc., and note that they are, you know, they have some risk factors for A, B, C diseases. And from a research-centric point of view, that particular genome sequence can be de-anonymized, I mean, can be de-identified, and just simply place of origin, racial, ethnic kind of, some relevant, you know, essential data could be codified, and the identity of the person wouldn't matter. Then this could be data mined and aggregated, etc. So, have I missed something? I mean, that's how I see it. So, what's the big problem?
Who wants to respond on the big problem? So the mic there.
So if I, does this work? Yes. So if there is a couple of issues with the solutions that you suggested in that. So first of all, it's very hard to understand what is the information that we should remove in order to successfully de-identify a genome, right? So the problem is that for instance, in the case of the science attack, so this data was de-identified, but using information that was publicly available somewhere else, like on genealogy websites, about people that were not necessarily the same as the DNA donors, it was possible for the researchers to actually find a link from a hereditary point of view between this information that was publicly available and the information that was de-identified. And you know, there are a couple of ways to do that. You know, one of that is linkage disequilibrium. So there are mutations that occur with you know, higher probabilities. Probably Jacques should explain that. So there is always going to be some information that is publicly available that might be used to trace back to the information that was, you know, de-identified.
But my question was predicated on destroying the data, but just noting the risk factors, which is, from a patient-centric point of view, what is useful.
Right.
And the rest of the data simply class-specifically noted. So there won't be anything to compare with anybody else's.
Right.
There won't be a whole sequence. You misunderstood my question.
Right, okay.
You have another mic, Jurgi, there.
No, it is a very good question. What people underestimate is that basically algorithms are constantly changing to analyze raw genetic data. Okay, and they are going to be constantly improved. So if, for example, on a full human genome now you would use the existing algorithms, you would be able only to detect 80% of the real genetic variants that are associated to a disease.
That's good enough.
And so if you like, this is why you basically need to, no, it's not good enough, because if you want to be, yeah, you know, and the applications are, the application you describe is a simple application. We are not there yet. So most of the applications are related to cancer, for example. And in cancer, the way you will tackle the data, it's very different. So any data you got, and the raw data, I'm talking really about the raw data, enables you to constantly improve the algorithm.
Very good. Maybe one question from the back, please, yeah. Yeah, go ahead.
Yes, but a small question.
Can you introduce yourself, please?
Oh, ik ben van Veen from the Netherlands. I've read these stories insofar as I could follow them as a simple lawyer about the de-identification, which were all very sort of theoretical cases. I mean, it could be done, but it could only be done because they had sort of access to those data from an inside point of view. My question is, what is the real chance that those data will be identified? Not as sort of theoretical exercises, but if they are kept well beyond lock and barrel, will then there be an inside intruder, because it was an inside intruder, as a matter of fact, they're acting like inside intruder, that they will be actually re-identified by someone with that vast statistical knowledge.
Very good. So about the objective risks, who wants to respond? Thank you.
It's tough to give you an absolute answer to that, because every circumstance will be slightly different. I would only say that it is, in theory, always possible to re-identify, and then you can make up the scenarios you want, whether it will happen or not. But the only limiting factor, let's admit for a minute that the genome of everybody in this room has been sequenced and stored in a central place. The only thing you need then to re-identify anything about anybody here is to get a cell from that person. And then you get a few markers from that DNA, and you go back to the big database and you get the whole genome of that person. And then you can deduce everything from that genome. So I don't think it's a minor problem.
So maybe you want to comment.
Yeah, maybe to add a point. From my regard, I don't know realistically what's the risk. But what I know is that I want this to happen, and I don't want to take the risk of this not happening and not being able to improve diagnostics and use these technologies due to a leak of information. And I think this would be a big risk for the application of such type of technologies. Discredit has to be considered very seriously.
Yeah, there have been all kinds of examples of real breaches, including against high-tech, really advanced IT companies. So the vulnerability of data storage is, I think, has been demonstrated. Yeah. Including data breaches in the hospitals, absolutely, absolutely. Let's take a question from Frank Kagel. Yeah.
Yeah, hi, Frank Kagel from Ulm University. I would be interested in basically what I would see as the biggest challenge to the work you do, and you've raised it yourself. I mean, if I have my little kit tested, and then there's whatever security protection to protect this data, or I have it sequenced, then basically the protection should hold at least, let's say, 80 years, if not longer.
Absolutely.
So do you have any idea how you could solve that challenge?
Emiliano, this is for you.
Well, that's actually an active area of research. So where we are aware of the fact that simple encryption will not help, but there are new techniques that actually have been are being developed in this area that actually entail adding some extra information. Like it's called honey encryption. That allows you to add extra information in such a way that even in the case of a compromise or in the case of decryption, you will not be able to reconstruct the plain text. But the problem is it's quite complex and is a challenge, and also entails the fact that we need to, as Effy was saying, need to combine, I think, privacy and security protection with trust. So we need meaningful system models to actually hold this data, right? But besides, the encryption. Yeah.
So it's a wide open challenge for cryptographers. There's no question about that. So we have a question over there, and then three on that side. Yeah, please.
It relates. So it's a revolution from what I heard. Okay, what you say. And today, we poor guys, we have PIAs for risk assessment, privacy by design to design the system. What is the status of this kind of work applied to genomics privacy? Do you know? Are we the starting point?
I think we are at the starting point, yes. There's a reason for us to meet here this evening, yeah. Who wants to respond maybe more generally?
I think it's a little bit early in the game to actually consider privacy by design, in the sense that a lot of the use cases that, for instance, my personal research agenda works on is not happening yet, right? So we don't yet have large-scale, whole genome sequencing for everyone. So we don't actually have, the business model or the system model outside, what Jurgi is working on, right? So, and I think they're taking probably, the steps in that direction with, privacy by design, models. But you know, with the other kind of cryptography-based solutions, we're not there yet. Yeah.
Yeah, so the body that would define those standards, I think, does not really exist yet. So all that has to be set up, essentially.
But we are maybe at a moment in history where, more than in many other fields, we can start doing it at the right moment. Right. Because Genomics England is 100,000. Yesterday night, Obama announced 1 million genomes before 2020. Craig Venter, the private pendant to Collins at NIH, announced 1 million genome before 2020. So for those 1 million genomes, we need strategies that are developed while they are sequenced, not later.
Just one thing I want to say, when we invented the internet, we invented an IP address, and you see the problem that it causes. So now, if you do genomics, you should not invent the IP address of the genomics because of the needs of that field. So this is very important.
That's exactly the point. So the idea is to learn from the history of the internet, the mistakes that have been made on that front. So there were three questions over there. Who had the mic? Yes.
Hello, I'm Espen from
sorry,
Norway.
you have to move on, yeah.
I just have a very quick question, because I'm wondering about what's the point of anonymizing it or encrypting it, because as you said, you only need one cell from one person, and to sequence DNA is getting cheaper and cheaper, and anyone can do it in 10 years, 20 years time. So is it really worth the effort?
Yeah, so that's a canonical question too. I'm glad you asked it, because it is important to be addressed. Yeah, maybe Effy, yeah.
Can I answer that, because the technology people, I'm sure, will have a better answer. But to me, as a non-special and as a non-computer person, it seems reasonable and worthwhile to make it as difficult as it gets. It might be possible to, do something, but I guess in all other areas of life, we do things that somebody could, finally commit a crime or do something which is really wrong, but we do have windows in our homes even if somebody's going to break in. So it seems to me a reasonable measure to take to make it as difficult as possible, and I think that's where probably you guys are going, and not impossible, but difficult.
Yeah, so maybe what don't you...
I mean, actually, I can answer with one word, which is scale.
Yeah.
It's the scale of attack that we ought to make different. So I don't know if anyone else wants to elaborate on that. I don't want to hijack.
Just if I can make one point on the API. I'm not sure, I'm not a computational scientist, but what I can tell you is that the reason we are involved in genomic privacy is that because it's not our business, genomic privacy. We are just doing privacy, adding privacy tricks to avoid any discredit. But the reason why we are acting there is because our algorithms need to be active, need to be able to analyze the data. And we want to influence it so that, exactly as you described, we don't protect the data in a way that is not going to enable make use of the data for the patients.
All right, so let's move on. Yeah, please.
Yes. My name is Josep Domingo Ferrer, and I work at the University of Tarragona, and I am an expert in anonymization. It has been said that anonymization doesn't work for this domain, and I think it doesn't work. Maybe it doesn't work. Differential privacy doesn't work either. I think that what looks, from what has been said, what looks like a bad idea is to centrally hold genomic data in the clear. Even storing it centrally in an encrypted form seems to be dangerous, because one cannot guarantee that there is resistance to decryption attacks in 30 years' time, for example. So you would, what the question is, do you think that it makes sense to hold genomic data in a centralized way, or should we rather go for each person holding the data in her personal device, and then when the person dies, just destroying the device, and that's over?
Absolutely. So I'm glad you asked. This has been envisioned as well, so who wants to respond to that?
That's envisionable, but we would lose the net benefit for humankind of making sense out of the aggregate data, and that's what is clearly missing right now. The reason why we cannot do genomic-based medicine at scale today is that we didn't learn even 1% of what the genome has to tell us. And to learn what the genome has to tell us, we need the data to be put together and to be analyzed in as large as possible data sets.
There was a third question in this corner, and then we come to you. Yeah, go ahead, please.
Philipp Schütz from the Fraunhofer Institute for Systems and Innovation Research. yeah, despite all the good intentions you have, and I believe that you have these good intentions for health reasons, I'm always thinking of DNA analysis as or DNA data as kind of Pandora box which you open, and first of all you can't anonymize, and then there's this huge amount of data which you actually can't make sense of at the moment, but you will be probably in the future. So we were talking about purpose limitation as a side comment. You said you only want to use that in a health context. But who actually is guaranteeing you that this is actually kept in that context? And I have a pretty good example where, yeah, this original context was violated. It's in Sweden, where since 1970, every newborn child has to give its blood sample to a huge database. And that was also just done for health issues. But when Anna Lindh, the Prime Minister of Sweden, was murdered in 2003, law enforcement agencies actually got access to these huge databases trying to identify the murderer. So I'm really wondering what's the safeguards in a system of huge data that entails, that comprises so many information that can be used, and there's huge interest in these information in the future. So we really have to be aware of that situation and to install safeguards that this is not possible in the future to have access to these data.
So we take a quick answer, then the last question, and we'll wrap up, yeah?
Okay, that's a good question, but the example you used from Sweden, it was to a reason to access the database was in a matter of fairness and justice, because somebody had to, the murderer had to be found. So there was perhaps a good reason for access, and it wouldn't be just some policeman going into the database. There's a process, and actually a very sophisticated process in getting that access. I think that example is where, you know, we might want to see. This is happening already, and there are good reasons for it. But I think your point is very important, because those data sets will be perhaps of interest to all sorts of interests, not to those who want to, you know, do it for the justice purposes, but for a lot more. And so the processes, I don't think, are in place, but the ones that should come to place.
Well, thank you for raising your point. I think it's indeed an important issue. Very last quick question, please.
Very last quick question, Charles Rabb, University of Edinburgh. It's in response to Emiliano's response to the question about privacy by design and PIA, and you said this is not the time to do it because we haven't really got there. This is precisely the time to do it. The philosophy and practice of privacy impact assessment and of privacy by design is to do those routines before your product, your system, your information technology gets down the road, at which point you may then have to retro-design it, which is expensive and stupid. I think that this is precisely the time when, and I'm not saying this with any malevolent intention, where you can anticipate the issues, the risks, the harms, as Effy was pointing out, and say, here is how we are going to mitigate those with these techniques and so on. And also, precisely because everybody has talked about nothing's going to happen without public trust. One of the big ingredients in getting public trust is to show that you have been proactive in doing a privacy impact assessment or something like it, and that you have designed in good privacy protection. Because then the public will say, why should we trust you? And you can say, well, you can trust us because here's the PIA that we did, and we'll show it to you, and you can tell us whether you think you trust us more than if we didn't do it.
Thank you very much. Thank you. Very quick response, maybe, and then.
So we have made it in UK, and I can share it with you.
Very good. All right, that's the response. Emiliano, you want to say something?
No, just want to clarify. I'm not saying that we shouldn't do privacy by design. My response was related to where we're standing with systems to actually build this system. So the philosophy under which we actually design our techniques, it really falls under the privacy by design techniques. Then on privacy impact assessment, you know, we can discuss it over a beer. I personally don't believe in them, but that's my personal opinion. So over a beer we can discuss it.
Okay, over a beer, that's the word of the end. Thank you very much for being with us, and have a nice evening.